Growing good crystals is an art. Apart from your science or apart from your research interest, growing crystals has its own interest and it has its own art. By this art, you can grow beautiful crystals because the crystals are the fascinating world. So you can get fascinated whenever you can see your crystals. That is actually your crystals are. So you have to grow the crystal. There are n number of ways. People might had about this. There are n number of ways to grow the crystals. Still, it is getting increasing, right? There are many methods to grow, but whatever it may be, now we are seeing only crystallographic webinar, not a crystal growth seminar. So I'm not going to in detail about the crystal growth. Among the crystal growth methods, I have taken only a small, a simple and powerful method. That is, you know very well, if you want to grow the crystals, audience or the research scholar who was very new to the field, you can get my words. If you want to go for a very simple method, you can go for your slow solvent evaporation technique. That is, you are dissolving your solid. You can take whatever may be your solid or whatever the things that you want to crystallize. You take that material and you get dissolved in some solvent where it can solve. Then you just evaporate the solvent. And now you have to take a control over the evaporation. That is the art. You have to do something. You can whatever the things that you want, you can do. For example, during my PhD work, my colleagues, my seniors will tell that they got crystals whenever they just put your uh, beaker inside the fridge. You can think in fridge, you can have very limited evaporation. But they got the crystals whenever they are putting that specimen inside the fridge only. Because they use that some medicinal samples or some chemicals, medicinal chemicals. The chemicals are maybe highly reactive to your atmosphere, or when it's exposed to the atmosphere, it may get contaminated. Because of that, when it is put inside the fridge, then only you can get your crystals. Right? So for that, you can dissolve and you can make a solution from your material. But how you are evaporating your solvent, that doesn't matter. If you evaporate your solvent in a controlled way, then the solvent will get slowly evaporated, then you will get beautiful crystals like this, right? Then there is another beautiful method. This method is very not popular as much as other popular methods. There is gel growth method. As if you want to grow some water insoluble crystals, if you want to grow some water insoluble crystals, this is a suitable method, or it's the best method to grow your crystals. Just you have to make a gel or a medium which consists of some pores, very small pores. Normally the people will take your sodium silicate or silica gel and agar agar gel. There are many other gels are available. They will take the gels and you can have one specimen inside the gel and another specimen in superannuated. That is, it is just to pour above that gel. Then the second material start to slowly getting down inside the specimen. Then you will get your crystals beautifully inside the uh, gel. So there are U-tubes, there is U-shaped tubes that can be used, because nowadays U-tubes have different meaning, right? There are U-shaped tubes that can be used, and also normal test tubes can be used to get your crystals. Whatever it may be, you have to attempt any one of the methods. It is not limited. You can go for any of the method that I have listed here. So you can go for any method in such a way that you have to find out how to get your crystals as a single crystals. After getting that single crystals only, we are going to start our X-ray diffraction work. Okay, how we are doing? You have to do your Bragg diffraction or X-ray diffraction. Whenever your D and lambda are inappreciable, then you will get your X-ray diffraction. Whenever the condition of your Bragg satisfied, then you can get your X-ray diffraction. How? So before going to that, I have to explain you two important things, but I cannot explain in detail. I just briefing you things. There is a term which is called as a reciprocal lattice in your crystals or crystallography. The reciprocal lattice is again an imaginary lattice, right? It is not a real lattice. And another one word, evolved. Evolved is a scientist who invented the concept, the lambda of your wavelength, by which you can get into know how your crystals will get diffracted and how your pattern will comes out. And he form a sphere that is nothing but a evolved sphere. You can see it on the diagram. This evolved sphere, that is, the radius of the evolved sphere is nothing but 1 over the lambda. That is normally it is called as a vector, k vector. And I'm not going to in detail about that theoretical point of view. I'm just explain you how this diffraction patterns are coming. That's it. How it comes. You can see here, you are getting lot of dots. How these dots are coming? It's very simple. Whenever the reciprocal lattice and your lambda, that is your evolved sphere, is meeting, then you will get your diffraction maxima or diffraction minima. See, the diffraction and interference are two different phenomena in your physics, but both are having some similarity in between them. It is a wave phenomena. The people very well know that it's a wave phenomena. So when the two waves are superpositioned, then we think about that diffraction or the interference. In interference, we told that you can get that your what you call your maximum intensity and minimum intensity, dark and bright fringes. In similar way, in diffraction, we tell that you are going to get maxima and minima. That is, you are going to get the maxima X-ray photons and minimum of X-ray photons. There is no X-ray photons in between this. You can imagine this as a film, or you can imagine this as a screen in which you are going to get the exposure of your X-rays, the X-ray spots, how it will be. That is explained by this small slide. How this explained? You can have a phosphorus screen, or you can have a CCD coupler, whatever it may be, and when you exposed, when that happens, when that wonder happens, then you will get lot of spots on the screen, right? How it look like? It will look like this. You can see there are a lot of spots. You can see that there are some spots, they are very dark, and there are some spots, they are very light, and you can see there is no spots in between two spots. Many other things are there. This you have to analyze. This diffracted spots that you have to analyze. A small, just I'm going to just explain a small uh, analyzing in your spots. I can say that. So you take this. What is the distance between this? And you just take inverse of that, then you will get a b value. And what is the distance of this? You just take inverse of that, then you will get a value. What it means? This distance in your phosphorus screen or your chargeable detector, whatever it may be, in this distance is arise only due to the lattice distance A. This distance is arise due to the lattice distance B. That is the explanation about this. So this is a small explanation that I have given, but still there are a lot of things. The each points are arising due to your Miller indices or Miller plates, H-scale plates. So you can account this each point to your Miller index. For example, I can say you can take some this point. You can say that this point may be due to the 435 plane or 012 plane or 102 plane or 112 plane. Whatever you can say that each and every point is related to some H-scale plane or Miller indices. That is the important thing. So what the thing that you are going to get from your X-ray diffraction work is very simple. You are going to get your H-scale planes and the intensity value. That is normally called as that is your intensity I and your standard deviation I0. This is the information that you are going to get it from your. I will show how that file will be. I have a file of your X-ray diffraction output. I will show that file in last. Okay. Then very simple. You are doing X-ray diffraction, you are getting lot of spots, and you are relating that spots, and you are trying to find out how your crystals are arranged at your atomic level or your atomic level or molecular level. So I can say that it is absolute and unique method to find your molecular systems or molecular structures or atomic structures. There are your find out your molecular assembly or atomic assembly. Still, it's a well proved method in your science and technology. Now, what are the inferences apart from your bond distance and bond angles you are getting in your crystals? You can get many other information. What are that? That you can get it your close packing, hydrophobic effect, hydrogen bonding, pi-pi interactions. There are many intermolecular, all possible intermolecular interactions you can find out, and by which you can develop a supramolecular structure in a system. And when we talk about that supramolecular structures, the hydrogen bonding are the important one. That is, like I mentioned here, hydrogen bonding are the important one. And the hydrogen bondings are actually joining your molecules, and you are getting that mm, beautiful crystals. And this hydrogen bonding actually making your material property, especially in a pharmaceutical specimen. If you want to improve the pharmacological efficiency of the drug, then you have to think about this hydrogen bonding. And Professor Desiraju from IAC done a lot of work on this hydrogen bonding, and his papers are mind-blowing papers. And the audience, whenever you are getting the time, you just go through the papers, and you may getting to know how your hydrogen bonding patterns are making many beautiful properties in your crystals. Then another important one, without saying that CST database, I cannot conclude that your crystallography or crystallography theory and experiment. So CST database, many of you may heard about, few of may not know about that. It is a Cambridge structural database or Cambridge crystallographic data center, which actually do that work. That is, when you are growing a crystal and when you are doing X-ray diffraction, after that you can deposit that crystallographic information file. That is nothing but CIF file. You can deposit the CIF file on the Cambridge structural database, and they will give you a unique ID for that deposition, so that you can claim that that work was done by you. It's a very nice depository, and there are more than now there are more than 10 lakh structures are available. There is this basically organic and metal organic structures are available, not macromolecular. It's only a small molecular. And audience, please keep in your mind that whatever the things that I have discussed so far, I might have told earlier, but now I'm telling you, whatever the things that we have discussed so far, they are only about the small molecular crystallography. We are not touching your macromolecular crystallography or protein crystallography, right? We are just talking about the small molecular crystallography. So this CSD, Cambridge Structural Database, is containing 10 lakhs crystal structures of your organic material, that is organic and organometallic materials. Then, so now the last part of my session. After that, I will explain you how you can solve the structure. Right? I will take hardly 5 minutes for this and 5 minutes for that, I hope. Okay. So I have not myself, and myself, my student did work on anti-cancer drug, which is known as mercaptopurine, 6-mercaptopurine, and we crystallized 6-mercaptopurine as well as 6-mercaptopurine hydrochloride. Both samples were crystallized, and we try to use many methods, but slow evaporation method only we got crystals. And you can see the crystals. These crystals are is not very nice crystals. It's very light crystals. So that means the thickness is very small, and you can see that you cannot claim it's a very highly transparent. So it's very, but whatever it may be, we are using a very small, less than centimeter, that is size crystals are used for your X-ray diffraction work. Whatever it may be your crystal size, it may have its applications in other sites, but as far as your X-ray diffraction is concerned, you require only few three-dimensional crystal, single crystal for your X-ray diffraction. Okay, because your material should be single crystal. That is, there should be a periodicity everywhere. Then that is called as your single crystals. So we got the crystals and we did that X-ray diffraction. I'm just going to expand this table, then I will switch over to that's your explanation session about your how you are solving the structure. This is the typical crystallographic output table that you can get it from any crystallographic work. You can start from that's the empirical formula, then formula weight. Empirical formula means what actually the molecular formula of the system is. Actually, we may think that we can get it from the just confinder, but this case for this table, we are getting that information from your output. That is how many your atoms are used for the refinement or solving the structures from which we are getting. There is many theory inside that I will tell you later. Then there's a formula weight temperature, in what temperature it was. Normally it is room temperature, hence it is given as a 293. What wavelength that we have used for the X-ray diffraction. What is a crystal system? Here you can see that both are monoclinic crystal system. But what is a space group? First one is C2 bar C, the second one is nothing but P21 bar C. And you can see that unit cell dimension of these systems. And there is a volume is given. Then you can see what is Z. Z, I already told you, number of atoms in the unit cell, which is nothing but your Z. Okay, here the Z value is 8, whereas here Z value is 4. Then you can see the what is the density. That is nothing but a calculated density. Here also, here also. This is only a calculated density. It's not actual density of the crystal. Then what is the absorption coefficient? Normally, this absorption coefficient should be a minimum value, because this absorption coefficient give you how much X-rays are absorbed by your specimen. Then this is an important one, F00. The F is the notation which is given, which is used in your crystallography as structure factors. This is F000. That means you are going to number of electrons in your system. Audience, please remember, when you pass your X-rays, your atoms are scattering your X-ray photons. That means it is just try to find out what actually the electron density map, how actually the electron density map inside your specimen, that is invented or that is actually found by any crystallographer in your X-ray crystallographic work. So the number of electrons in the system is very important. Okay, so this is the number of electrons in this molecular unit. This is the number of electrons in the molecular unit. Then what's the crystal size that is used for your X-ray diffraction? You can see that it is 0.2, 0.2, 0.25. That is very, very, very minimum. It's a 3-dimensional. In one direction, other direction. What is the size of your crystal? Then angle, what angle that we have employed. Then what is the H scale limiting indices? -18 to H will start from -18 to 18 and etc. etc. So on. And another important point here is this one. What is this reliability index? Or actually, this is very important. Whenever you are doing your crystallographic work, that reliability index R should have a very minimum value. If your R value is greater than 10, we can say that your crystal is not converged, or your structure is not proper, or we can say that it may be your correct structure, but your X-ray diffraction work is poor. We can say that it may be a correct diffraction, but your crystal may have some tuning or some improper orientation, or it is not a proper crystal. Because of that, there are many reasons that you may get your reliability index to be very poor. But a good reliability index definitely ascertain that the compound is that. That's it. That is, you can confirm the compound by this good reliability index. That is, if your reliability index is 2.89, here you can see that 2.89 means 2.89%. 0.03, you can say roughly it is 3% or 0.03, then definitely this compound is right, by which only the people try to identify. You can see here I have deposited to this Cambridge crystallographic data center, and we got the number for that also. For these two we got the numbers. So apart from that, you can get many beautiful information about your molecular structures, its packing and other things, right? Then this gives you how your atoms and molecules are oriented, or how the atoms are connected inside your specimen, etc. And it's go on, right? I'm not going to in detail about this because it's just explaining, or it is used to for your applications how your molecules are connected. Now we are not going to publish anything, we are just explaining the things. And you can see that here your molecules are connected. This is your mercaptopurine molecule. This is your chloride. How this connected, that is explained here. And it is another perspective, or in the another view, you can see that the molecules are arranged like a corrugated states. Okay, we just leave it. So with this point, I switch over to an important session of this meeting. I feel that is very important. That is how you can solve a structure, right? I hope everyone can see my desktop screen very clearly. How we can solve the structure, right? So here there is a tool which is known as your WinGX. Using the WinGX, you can solve the structures. For solving the structures, I'm going to take a compound which I have published very earlier, nearly in 2012 itself, done by my colleague and my friend. You can see that this is creatinum hydrogen oxalate. This is a compound. You can see there is a compound. Now we are going to solve the structure. Okay, very simple. 5 minutes explanation. I hope I can complete. Okay. How it can be solved? First, you have to get that creatine molecule. Then you have to mix it with the oxalic acid. Then you are getting that creatine oxalate, creatininium oxalate, and it is called as because it is protonated. I will explain in detail about later. Now you got the crystal and you are doing some X-ray diffraction work. Okay, well, you have done the X-ray diffraction work. What you will get it? You can see this is the output of any diffraction or any X-ray diffraction work. You can see that 100 plane. What is the intensity? 17.29. And it goes on in 700 plane. You can see that 131.27. It goes on. It goes on. And you can see that there are many lists. The list will go to maybe 8,000 reflections may be there, 10,000 reflections may be there, 25,000 reflections may be there. That depends upon how your molecule is big and how your crystal has the indices, H scale indices. That depends upon that only. Okay, so this is a typical output of any crystallographic diffraction, that is crystal diffraction work, right? Okay, you got it. Now how you are solving the structure, that is important. You can see here I am using WinGX program, and if you load your program, another thing it will ask, that is what actually the instruction that we have to give. You can see that normally you will get that instruction file also from that X-ray diffraction work that we are doing. You will get these two files only. After loading this instruction program and our instruction file, I can say that instruction file and this HKL file, if you go solve and using that software, there are many softwares are available. I'm just using that SUR 2004. It is very older one, but it's working good. And if you apply your files, it will just gives out, because nowadays the computation technologies are working very well. Okay, you can just congratulations, the structure is likely to be solved. Very simple, right? You can see here. Now you can see orientation. This is nothing but your oxalic acid, right? This is nothing but your oxalic acid, and this is nothing but your creatinine molecule, right? These are some Q peaks, means that is nothing but electron density. That's how the peoples are solving the structure. See, keep in your mind, it's not a very unique way to solve the structure. There are n number of softwares are nowadays available. You can use any software, but the output file that you are getting from your X-ray diffraction is HKL indices and the intensity. And you are going to get the instruction file also, because the instruction file normally contains your ABC values and etc. Right? So that's how we are getting our structures. Now you can see that you are getting the structures, and of course still two more steps are there. You can export the structures to wherever you want. Then you can see the structures here. You can see here. You can see here. Right. It may be very slow in some screens, but you can very clearly see that the structure is solved. You can see this is nothing but your creatine molecule, and this is nothing but your oxalic acid. And still there are many steps are involved, and you can refine. This is only just solving the structures. After solving, you can refine and you can get your complete structures. And of course, there are many softwares are available to visualize your structures also. I can show you. You see here, there is a software which is known as a Mercury. You can see the salt structure, and this is not a refined structure. Keep it in your mind. It's not a refined structure. It's only a salt structures. Okay. After solving, it require a lot of steps to be done, and you can get the completely refined structure with proper reliability index value. I told you when the reliability value is less than 5, it's perfect. And if it is less than 7, then it's okay. If it is going more than 7 without any reason, or 10, then we can tell that it's not good. You can see the molecule. I can see the molecules. Yeah. Okay. It is a solid structure, but still we have to go a long way, right? Okay. So what we have discussed and concluded our session. So whatever the things, it consists of only 3 steps. Okay? You have to know the system, and you have to do X-ray diffraction and solve the structure. Then you can put
Sir,
your
participant, please mute.
I hope with this I can complete my
Participant,
session.
please
I
mute.
hope Suresh, I hope I can
Sir, please share only
stop with
slides.
this session. And
Yes, sir. Yes, sir.
um,
Hello.
okay, so first I thank you the audience. I came to know from Dr. M. Suresh, PMC Tech, and Prabhakaran that there are overwhelming response for this webinar. We didn't expect this actually, but there are more than 1,000 registered candidates for these webinars. And I thank you all, and I thank you all for giving me this wonderful opportunity. And I hope I have explained a small thing. I hope I hint you towards the crystallography work. Still we can learn many things. Still I feel that I am a learner in the crystallography, so you people can learn many things fastly, this crystallography, and you can do a lot of very good crystallography work. And thank you one and all. And anyone who have any clarifications or anything, you can make that clarifications through my WhatsApp number that I have given here, and also through my email. It's most welcome. And if your organizer is willing to make some chatting session or any question and answer, then I am very happy to provide. Now I hand over the things to the Dr. M. Suresh and
Thank you,
Prabhakaran.
sir. Thank you very much. I was planning for a small question session. If some of the candidates, if you are able to ask question one by one, we can clarify that here itself. Can we have any doubts
Now,
here?
I think you have to unmute all, right?
No, no, sir. Please put your questions in chat section. Based on that, we
Okay,
will
in that way,
clear it.
right. Okay.
With their name, sir.
Yeah, please, participant, please put your doubts in the chat section with your name, and we will unmute you, please. In this juncture, I would like to thank Dr. S. ATHIMOOLAM for providing this great opportunity for our community and the people, those who are working in this field. Sorry for the inconvenience caused during this session by the technical issues. And once again, I would like to thank all the participants, those who all put their great effort to reach here, because as our resource person mentioned, almost we had a registration about 1,500. We are not in the position to serve all. Still, we are having full confidence that we have served to some extent. We are planning to post this recorded version in your YouTube channel, and we are going to share the link to your everyone. And if
Nice.
anybody having that separate doubts, you can ask that doubts in our communicated mail or with our Dr. S. ATHIMOOLAM. Can I have that interaction session, sir? Anybody posted any questions? Hello?
I think no one is posting any questions on chat session. Okay,
Yeah, yeah. Sir, some question is here.
Yeah. Which method is best, either Lavey pattern or single crystal exotic diffraction? Okay, Lavey
Yeah.
pattern it's not applicable nowadays because Lavey pattern gives you only ABC values or initial values. You have to go for complete single crystal exotic work only. I hope who is that the name of that person? I hope I have
Arun
answered right.
Kumar. Arun Kumar. Arun
Yeah,
Kumar.
Arun Kumar allegation. I hope you understand that my point, because Lavey pattern will give you just your, because there are Lavey pattern, there are precision cameras or Lavey cameras are available older days. Today we are using advanced computing system or advanced diffraction diffractometers, which within an hour or within 2-3 hours you will get your entire structures. So the Lavey pattern is nowadays not at all preferred one, or it is not that much useful that we think. Then another one question from J. Thirumalai: what is reducible and irreducible representation of the crystallography? Okay, it's very simple. If a unit cell can be explained with a primitive cell, that is, there is a only one. Okay, one one atoms in the unit cell, and if you are choosing it as a two, then that is nothing but bigger cell. So you can reduce that. In that sense, it is called as a reducible cell, right? Some cells can be reduced and some cells cannot be reduced. Still, if you go for in technical, I can tell you, and that is a C2 bar C and P2 bar C, both are similar space groups. One is multiplication of others. That's it. Okay. So it does only your how big your chip is. Thank you, Thirumalai. Next.
Sir,
Any
one more
questions?
question from Mr. Muzaffir Kani. He is raising the question. Where it is?
Yeah,
Yeah.
please.
Polymers always amorphous in nature. If converting into metal complexes, what are reasons behind this one? Some more polymer or crystalline?
Okay, see, polymers are normally your organic specimens. When you join with your inorganic specimen, that is your metal. Metals are prefer always your crystalline nature. When you just join together, then you get your metal organic. But definitely that metal organic will not have the properties of your polymers. And this metal organic will not strictly follow your metal properties. So it is only your choice. It is only your choice where we have to go, how we are going to use. Okay. Software for any free software for visualization the crystal structure and property. Very simple. Mercury. It is very freely. Keep in your mind, your HKL file is only a data. It is not. It cannot be visualized. You can
1 minute,
visualize
1
only
minute, 1
structures.
minute, sir. 1 minute,
Yeah.
sir. Sir, the
Please.
participants, everyone, participant.
I think I have answered, right?
Yes,
A question from Pankaj Scott Gay. Hello, sir. Which is the simplest method to grow crystals? Slow evaporation or SR method? Simplest means slow evaporation, but SR method has its own advantage. It's a very good method, and it is our in-house. That is, it is came from India. No, we have to proud about both pillars of the crystal growth. That is Sankaranarayanan sir and Ramaswamy sir. PR method is a very good method for growing bulk crystals. As far as the crystallography is concerned, slow evaporation itself is sufficient, right? Any other questions, please? Suresh, can you hear me?
Yeah. 1 minute, 1 minute. Yeah,
Yeah,
one more
I
question
think
is.
there are many questions. Yeah, please.
Yeah. One or two
Two
last
more
questions, sir.
questions. Okay,
Yeah,
one or two questions, please.
kindly tell the range of R factor, uh, whether it explains the quality of the crystal.
Yeah, of course. The R factor, it explains the quality of the crystal, quality of the data, as well as how it was solved. It depends upon three factors, not only the quality of the crystal. Okay. Yeah, the R factor value is, it is less than 5. I think the question is posted by Arun Kumar allegation. I
Yeah.
told you that the R factor is less than 5. then we can say that the structure is correct. That's it. You are just confirming the structure. Okay, it's not the question of the quality of the crystal. If you want to find the quality of the crystal, there are some methods. There are some rocking curve methods, or you can use some polarized seeds, and you can see the crystals, how your crystals are good. There are some other methods, but R factor is a factor. It involves three different things. One is your quality of the crystal, as well as your diffraction data, how it was solved. Okay.
One more question, sir. Dr. S. Sudarshan,
Please. Okay.
can we use the same method to solve both 2D and 3D crystals?
Can
This
we?
question is, can we use same method to solve both 2D and 3D crystals? Dr. Sudarshan, I can't get you.
No. Actually, what I hope what he asked is the 2D crystals means there is a thin film layers or the layers of the specimens. For that we can adopt that. No, the 3D crystal structure is something different from the 2D crystal structures. You cannot apply both in the same way. Okay.
Hello.
The
Any
last
other
question, sir.
questions?
Yeah, yeah. Hello. Somebody raised the question in last.
Please.
Who is that? Can you
Yeah,
please?
please. Yeah.
Hello.
Hello, I can hear you, Suresh. Please proceed.
Somebody came in voice, but they can't get the line. Okay. Anyway, I'm going for the last question. Okay. The question is from.
Hello.
Yeah, please.
Yeah, please.
Proceed.
I think I can hear. Please.
Is there any free softwares for finding out the lattice constants and X-ray density, porosity, like that?
Okay, see, if you want to find out your lattice constants, first you get to do the X-ray diffraction. There itself you can get your ABC values. You cannot simply sit on the computer and you can get your lattice constant values. That is not possible. Can you understand?
Yeah, I can understand, sir. But after getting
Yes.
an X-ray, after getting the XRD pattern,
Okay.
getting the lattice.
Wait, I will tell you. If you are getting the XRD pattern means from the powder XRD pattern you are asking, or your single crystal output?
No, not in a single. It is in a powder XRD.
Okay, the powder XRD, there are many softwares are available. Actually, that topic is not covered in this seminar, but even then I can tell you, I think there are Jana, there is a software which can work and you can get your ABC values.
Oh, so
Many
it is
softwares
free.
are available.
Yeah,
it is free. It is free, but
So
it
can you
requires
give
some pre-registration.
Okay. So
No, I
can you
couldn't hear you.
free software?
Hello, the software name is JANA. Okay, Jana.
Hello. Hello.
Yes.
Hello, sir.
Please go ahead.
Good afternoon,
Go
sir.
ahead.
Good
Sir,
afternoon.
what is the difference between FTIR and Raman spectroscopy studies?
Again, the same. Okay, these questions are different from this topic, but even then I can answer you. You know very well in the school days, FTIR it's working on your dipole moment concept, and it is only your Raman scattering is working by the means of your polarizability. Okay, both are complement to each others. Some of the lines that won't come out in your IR spectrum, it will be available in your Raman spectrum. Okay, sometimes both the lines may be available in the both the spectrums, right?
Okay. Okay, sir. Thank you so much.
Okay, thank you.
Okay. So I think we can close here. And if you have people, if you have any more doubts, you can mail to Dr. ATHIMOOLAM. I think he will definitely reply to you. I think he already shared his communication details. In this juncture, I would like to I like to end up this session with a lot of thanks. In this juncture, on behalf of all of you and behalf of our institution, I would like to thank Dr. ATHIMOOLAM for spending his valuable time for us. Hope to have you in the future session also. What we are planning near future, sir. Thank you very much, sir.
Okay.
And in
Thank
this
you.
juncture, I would like to
Thank you,
thank
Anand.
Dr. S.P. Prabhakaran, who is my colleague, who
Organize.
took all his effort to arrange this program. Once again, I would like to thank everybody. Thank you all.
Thank you all.